So today's lab is going to be on determining the density of an unknown liquid. So what you're going to do is you're going to get a liquid, and you need to determine the density of it. Basically, the mass and the volume to determine the density. And the way we're going to do that is we're first going to calibrate our 10 mil graduated cylinder. So that's the first part. We're going to figure out what is it exactly how much our volume is when we fill it up to 10 mils. I know you would think it's 10 mils, but it really isn't. There's error in it. And so we're going to gravimetrically determine that, which means we're going to be using mass. Once we do that, we're then going to determine the density of our unknown sample. So how are we going to calibrate this? Well, there's a kind of a stepwise procedure here, and then we're going to repeat these steps. But it's fairly simple. The first thing you're going to do is you're going to get a 10 mil graduated cylinder. So you grab that, make sure it's dry. And then what you're going to do is get a 250 mil beaker and fill it up with 250 mils of water. You're also going to place a thermometer in it. And you want to put that thermometer in it because you need to know the temperature of it, which we're going to record in a little bit, which is exactly now. So once that thermometer comes and is able to read the temperature, you're going to record that. And so that's going to go right there. And so you record your temperature. So far, so good. Pretty easy. Step 4. You're going to take your graduated cylinder, empty, dry and empty, and you're going to weigh it. So you're going to get its mass. Once you know the mass on our analytical scale here, that's going to go into that. Notice this is going to be the same for both run 1, 2, and 3 because you're going to be using the exact same graduated cylinder. At this point in time, you're going to take your 10 mil graduated cylinder off the balance and fill it up to the 10 milliliter mark with just that deionized water from the 250 mil beaker. So you're going to put that all in there. Once that's filled up to the level of the 10 mil mark, you're then going to reweigh it. So you're going to take your graduated cylinder with the 10 mils, weigh it out again. Once you know that, that's going to go there. So all we need to do then for this part A is repeat this. We're going to retake the measurement of the temperature of the water after we dump out so we take our graduated cylinder that we just had, dump it out, take the water's temperature again, put it here, fill it back up to 10 mils of the graduated cylinder, and reweigh it. We don't have to reweigh it empty because that's why we did that first weighing by itself. Once you get 3 trials, you can then move on to part B. Notice line 2 is taken out because you can just copy that mass from part A. So how do we do this? Make sure, number 1, you fully dry out your graduated cylinder. You want to either use a little bit of ethanol or acetone to get rid of the water, air dry it, but you want to make it really, really dry. So first things first, in our data, we're going to copy over the mass of the empty graduated cylinder. So that's from part A. The next thing you're going to do, now that you know that, is you're going to take this graduated cylinder and you're going to fill it up with your unknown to that 10 mil mark. Once we have that filled, you take your graduated cylinder again, filled with your unknown, and you weigh it out. You get the mass, and that goes there. Okay? So once we have that, we then know the mass of that sample because we can take the 2 and subtract them. All you got to do is that 3 times. Dump it out, dry it out, fill up your unknown, weigh it again. Dump it out, dry it out, fill up your unknown, weigh it again. Done. At that point in time, once you have all your data, you can just complete the calculations and the post-lab questions fairly easily. And then hopefully you have enough time to submit the data online. A word of caution. There is a tricky calculation here because if you look at your data, you're determining the volume of this graduated cylinder when you fill it up to the 10 mil mark. You would think it's 10 mils, but it's not. Okay, there's always error there, and so you're calibrating this. So you're doing that with water, and the reason why you need to know the temperature of the water is that the density of water changes with temperature. So it's not really one. So what we can do is we can come up with an equation that puts this in between. Well, how do we exactly do that? Well, we can see the temperature is relatively large, but the density doesn't change very much. So if we assume that this is linear between the two, we can actually graph it. So this is my 20 point, this is my 25 point. We can come up with an equation for this line, which we see here. This gives us that equation, and what this produces is a relationship, a linear relationship between temperature and density. So that means if we don't have 20 and we don't have 29, but what if we had 21.3? Because you're not going to use the density at 20. Can't use the density at 25. You got to come up with this equation. So what this allows us to do is say y-axis, which is density, is equal to the slope multiplied by the x-axis, which is temperature, plus our constant. If we plug in our 21.3, this gives us the approximate density of water at 21.3. So kind of take that all in. This all assumes that this relationship is linear. And in fact, it's not. It's actually curved. This is the plot of water. This is the density of water per degree Celsius. We're only like here. So what we're saying is that this point here is fairly a straight line, and it actually is. If you take 2 points that are close together, we can always model that as a straight line. In reality, it's not, but the way we're looking at it, the very first approximation is that we can assume that it's linear. But if you look at it over a long temperature change, you can see that really isn't that linear. There's a curvature to it. But we're just doing a first approximation.